Okay, hello everyone. Let's get started. So the calculations can be a little bit complicated, but we're going to go through them step by step. So let's begin. Okay, so so today's experiment is, so we're just going to do step by step here. Standardization of sodium thiosulfate. Okay, so our standardization of sodium thiosulfate, we need to be sure to write the balanced chemical reaction, okay? So first, let's write the balanced chemical reaction. It looks a little bit complicated, but if we just go step by step, it shouldn't be too bad. So IO3 minus. So everything is in the aqueous phase or liquid here because it's occurring in water. Okay, so what's happening here is we are doing a redox reaction and it's catalyzed by acid. So that's why we add the HCl. It's catalyzed by this acid and we get the reduction that's happening is, or the redox reaction that's happening is you're going from I2 or I minus to I2, and then you're going back from I2 to I minus again in the second reaction here. And we get I2 aqueous plus H2O liquid. So let's see if it's balanced. So we have 3 oxygens here, 3 oxygens. So let's go proceed to balance this equation here. Okay, so what should we do first? Okay, so right now we're balancing iodine, right? But we're not balancing oxygen. So maybe we should balance the oxygens first. So let's put a 3. So I'm going to do a different color. 3 in front of the oxygen. All right, so now we have 6 hydrogens and 3 oxygens and 2 iodines. Okay, on this side of the equation, we have 2 iodines, or sorry, let's go back in order. Now we put a 6 in front of here because we need 6 hydrogens, so 6 hydrogens. Now how many oxygens? 3 oxygens. And now we have, let me just put a little space here so they don't look like numbers. And 2 iodines. Okay. All right. So are we balanced here? Looks like it. No, so we might look chemically balanced, but we're not because this side has a charge of 0. So in redox reactions, we also have to consider the overall charge. So this is a 0. And this, however, is 5 plus. So we're not actually balanced yet. See right here, it says 5 plus. 6H plus minus 1. Actually, it's 4 plus. Minus the 2 negative charges there, that's only 4 plus. So we actually have to make sure this is neutral. And to do that, we can do, let's see here, we can make this a 5 because if we times 5 minus plus -1, that'll give us -6. So now our charge is 0 here. But we're not balanced yet because now we have 6 iodine molecules. So we need to put a 3 in front of this I2 here. And that will give us 6 iodine atoms here. So there we are finally balanced on this equation. Okay, so that's our balanced equation for the first one. Now let's do the second one. Okay. So the first reaction, you react iodate with iodide. It forms some iodine and some iodide will be left over. So what happens is the reaction that the color you see, so the brown or brown maroon color is due to this reaction, I minus plus I2 to give me I3 minus. So I3 minus is this molecule here, the triiodide complex here. So this is called the triiodide ion. So the let me just space that out here. Triiodide ion. And it's a red-brown color, depending on how concentrated it is. So red-brown complex. Well, I want to call it a complex. Let's just say it's a red-brown ion. In aqueous solution. Okay, so it appears red-brown, and that's the color you immediately see as soon as you add everything in. So as soon as you add the iodate, the iodide, and the H+, there's some equilibrium established. So this is what you see, the triiodide ion. And then it's this ion that when you connect it to starch, it turns dark blue. And that's where we want to figure out where our endpoint is, because now we know we have some starch form. As soon as starch gets titrated, this equilibrium will form more starch until eventually all your iodate is used up, and that's where our endpoint tells us how much thiosulfate we added. Okay, well, anyway, let's go to the second reaction now. It's I2. So we form the I2. So you see in this equation, we form the I2 plus thiosulfate. So thiosulfate is used to titrate this molecule here. Very different from sulfate. Sulfate would not do this. And then you get the iodide again. So the thing about iodide is that it's not it won't complex to starch. So once you have all iodide, it won't interact with the starch at all, and that's why it appears colorless. And then you get the tetradiiodate ion. This ion right here. Okay. So in this case here, we get S4O6 2 minus aqueous. Okay. All right, so let's balance this reaction. So these are redox reactions. Maybe we should go ahead and write the redox numbers on this first one here. So this is plus -2, and this must be plus 5 to give us an overall charge of 1, -1. This is -1, same as the charge on the ion here. This is +1. Let me write them in red, actually, so they're easier to distinguish. So here are my redox numbers in red. -2 plus 5, -1, +1, 0, and then -2, +1. As you see here, my oxygen is going from -2 to -2, so that's no change. My hydrogen is going from +1 to +1, so that's also no change. But my iodine is going both from +5 to 0, and also -1 to 0, or to 0 as well. So this is where my oxidation is happening. So this is oxidation, and here's my reduction reaction. So this is a redox reaction. So sometimes in redox reactions, you can have both the same element going to different oxidation states. That's what we call. There's a certain type of reaction for that, but it doesn't actually qualify here. But so I won't comment further. But there's situations where the same element goes to two different oxidation states. All right. All right, so let's balance this reaction here. All right, we need 4 sulfur atoms. So we have 4 sulfurs right here, 6 oxygens, and 1 iodine. So it might be best to balance the sulfur first. So let's put 2 here. So now we have 4 sulfurs, 6 oxygens, 2 iodines. And the charge here is now -4. And the charge here is -3. Okay, so to balance this reaction, we should put 2 on the right side because we have only 1 iodine on the right side. So let's put 2 there. Actually, let me write these in blue again. So we have 2 and 2. Oh, sorry, not there. Right here. So now we have 2 iodine atoms. So now our total charge here is -4. So I think we're balanced now. So our reaction, this is our balanced chemical reaction. I2 goes to 2 molecules of thiosulfate, gives us 2 iodide ions, and tetradyne. Let me just Google this real quick. What is this ion name? I've seen it before. Tetradionate. Yeah, so it's tetradionate, I believe. Right, so tetradionate ion. Okay, so that's the tetradionate ion. If anyone's wondering, this is tetradionate ion, and it's actually the conjugate base of, it's like sulfuric acid. So it has an acid form of H2S4O6, but a very different acid in terms of structure. Okay. So by forming the triiodide ion, we can monitor the latter reaction because it allows us to determine the color change, because with starch, as we know, the triiodide ion and starch forms a blue color, and iodide will be colorless. So this will be, the iodide will be, so iodide by itself, colorless with starch. And then this guy will be blue complex with starch and iodine minus. Okay, so the amount of iodine forms will combine with iodide and form this complex with starch. And as soon as the reaction gets titrated with thiosulfate, that complex will disintegrate, and then more iodide will combine with iodine, or more of it's reduced, combined with iodide, until eventually all the iodine is reacted with the thiosulfate, and then you get your endpoint. Okay, so that's our that is our reaction there. Okay, now let's go to the calculation. So that's what's the first part of calculations. Okay, so we're going to standardize our thiosulfate solution. Okay, so our thiosulfate solution should have been 0.05. Okay, so 0.05 molar solution. Okay. Okay, so the first thing we do is we're going to now standardize our solution. So let's go to part B. Moles of potassium iodate. All right, so we prepared a molarity of 0.01 molar KiO3. Okay, so we measured that out and formed a solution of it. So you're going to use both your molarity and your volume. And your volume should have been 5 mils. Okay, so 5 mils. So we're going to take this volume and multiply the molarity here. Okay, so we have 5.0 mils times 1 liter gives me 1,000 milliliters in a liter times the molarity 0.01 moles KiO3 over 1 liter. So that's what molarity would be. Okay, let's just double check here. We use 5 mils of our solution. Yes. And then 0.01 molar KiO3. All right, so everything's good. Okay. So that will give us a value of, all right, let me pull up my calculator here. So that will give us a value of 5 divided by 1,000 times 0.01. So that gives us about 5 times 10 to the negative 5 mole KiO3. Okay, so that's our mole. So let's keep our units. Actually, that should actually be correct. The around 6 figs there. Okay, so that's how many moles of KiO3 in solution. So in each titration, we have this amount of KiO3. So that's our amount of moles there. Okay, so taking that number now. Okay, so now to determine the moles, so remember at the endpoint, the moles of our titrant equals the moles of our analyte, right? So at equivalence point, moles iodine minus equal moles S2O3 2 minus. So that's our little key here to solving this problem. So now we can take our moles of iodate and say, oh, how much, and use our balanced chemical equation up here to figure out how many how much thiosulfate we have. So there's a couple things you can do. You can convert it to iodide, moles of iodide using balanced chemical equation, or you can just convert it to iodine. Since we're doing, since iodine is what's being formed in, as our limiting kind of reactant for the second step, we can just do that. So we notice that for every mole, 3 moles of iodine, we get 1 mole of iodate from our first balanced chemical equation up there. So we have 1 mole iodate over 3 moles iodine. So notice we cannot directly take convert iodate to thiosulfate because they don't directly react with each other. So we can't do that. We need to use 2 conversion factors in succession. Okay, so iodine, and then the common factor here is iodine, or in this case, or iodide. But you see here in the second reaction, for every mole of iodine, we react with 2 moles of thiosulfate. So we're going to put 1 mole of iodine will give us 2 moles of thiosulfate. Okay. So if we just solve that, we'll find our moles of thiosulfate that was used to react with iodate. Okay. So now let's go over the calculation again. We get times 3 times 2, so, or times 6. So we get 0.00003 moles thiosulfate. Okay. So that's how much moles of sodium thiosulfate that we have in solution. So even though it says, so even though it's in the chemical equation, the balanced chemical equation, even though it doesn't have the counter ions, that's okay because you know, for each iodate we have the same amount of KiO3 in there because it's a 1-to-1 ratio. 1 mole of it will give us that many moles of iodate, and likewise here. We could say S2O3 minus, but as you know, this will be the same as writing sodium thiosulfate, because for each mole of sodium thiosulfate, we get 2 moles of sodium ions and 1 mole of S2O3 2 minus. Sorry, it should be 2 minus. 2 minus right here. Okay, so it's the same thing in this case. So now we have our moles of thiosulfate. We were able to determine our moles there. Okay. So to determine our molarity, so that's part B. Let's make this part C. So that's moles of, so here is moles of sodium thiosulfate. And then we have part D here is the molarity of sodium thiosulfate. So our molarity, we have the moles over liters. In this case, we're going to use our volume as the equivalence point to determine the molarity. Because, you know, when we add the solution of thiosulfate, we're adding a known volume of it. So if we know the moles that we added in that volume, that'll give us the molarity. So moles of S2 O3 2 minus over, well, let's put sodium in the mix. Okay, so your volumes may vary. I'm just going to use a one made up. I didn't want to observe from class, so I'm going to do 5.65 times 10 to the negative third liters, because that would that we need to put it in our liters, right? So if my equivalence point volume is 5.65 milliliters, then in liters it would be like so. 0.005123, yeah, 65 liters. Okay, so let's calculate that now. So we would get a value of divided by 0.00565. And that's a molarity of very spot on, but you see here it's slightly above 0.05 molar, 0.0. So let's go a few digits here, 0.5. So let's put 3 sig figs, 53031. Because we know the volume to a very accurate amount because we measure out 5.00 milliliters. So let's do that as well. 3 sig fig, so 0.0531 molar. So pretty good numbers. So this is our answer here. All right, 0.053 molar of our sodium thiosulfate. Okay, so repeat this calculation for all 3 trials. So repeat these calculations for all 3 trials for part 1. Okay, so for part 1, we're going to repeat all these for the 3 trials for part 1. All right, and then calculate average molarity. Average molarity, standard deviation. And 90% confidence limit, 90% confidence limit. Limit of the sodium thiosulfate solution. Okay, so we're going to calculate all those values here. So remember, equivalence point volume is where when solution turns colorless after starch is added and you form a blue color. Okay, so if you add the starch and you immediately get a color solution, something probably went wrong, and that means there's no more starch in there. So you would discard that trial and just do another one. Okay, so that's molarity. That's part. So this is the end of part 1. So this was part 1. So here's A, Okay, so balanced chemical reaction, find the moles of iodate, determine the moles of sodium thiosulfate, then find the molarity by using the endpoint volume or the equivalence point volume. Okay, so let's go to the second part now. The second part is where we now are going to get into calculations of the KSP value. So calculating. So we're going to calculate solubility so solubility X So the thing about KSP allows us to calculate the solubility of an ion in solution. So calculating solubility of calcium. So the data for the first 3 trials of part 1, that's only for part 1, so you don't need to use them anymore in these further calculations. So for the endpoint, so for this one, you want to record a few things. So A, what is the volume of standardized volume of standardized Na2S2O3 was required to reach the endpoint. Okay, so you're going to use this, these values here. You're going to use the value of the endpoint in this reaction of the saturated calcium iodate in pure water. So you're going to use the volume from part 2. So this is from part actually this is part 4. Sorry, I think this was part 2. We should have said this is for part 3. My apologies there. So this is actually part 3. Part 1 and 2 was making the solution. So we all did that. So no need to refer back to that part. So this is part 3. This is part 4. Okay. So you're going to use the volume. So A, find the volume required to reach it. For example, maybe mine was, I don't know, let's just say it's 6.80 milliliters. Let's just say that, okay? And then we're going to find the moles of sodium disulfate that was added at the end point, or equivalence point, sorry. So we have, so now we're going to find moles of sodium disulfate equals molarity times liters, which gives us 0.0531 molar times 0.00680 liters. Okay, so that gives us a value of, all right, so let's go back to our handy calculator here. 0.0531 times 0.00680. Okay, so that's about 0.00361 moles sodium disulfate. Okay, so now we found our moles of the sodium disulfate. Now we need to backtrack and calculate the moles of iodate in solution. So C, we want to back calculate and use the balanced chemical reaction to find the moles of iodate in solution. Okay, So what we do first is look at the balanced chemical equation. Okay. So we know that we have 0.00361 mole sodium thiosulfate. Okay, so that's moles of sodium thiosulfate. Now we go back here to chemical equation here. We know that two sodium thiosulfates will react to form iodine. So for every 2 moles of sodium thiosulfate, we get 1 mole iodine. And if we look back to the other equation up there, we see that for 3 moles of iodine, we get 1 moles of iodate. So essentially, you're just going backwards and making dividing everything by 6. 1 mole iodate. Okay. And if we solve for this, we just divide the number by 6. Divide by 6, and we get 6.02 times 10 to the negative 1, 2, 3, 4, 5. 5 molar iodate ion. So this tells us the amount of iodate that was in solution is 6.02 times 10 to the negative 5 molar iodate. So in here we found moles of, let's just move everything down a bit. Moles of iodate in solution. And we could probably erase these sodiums. We probably don't need it. Let's just write the ion instead. Okay, so that's our answer for this part. So let's just highlight a few things here. Actually, it's okay. We're good. All right, so the last part of this is you're going to use the number of moles of iodate and the volume of saturated calcium iodate in water to calculate the molarity of IO3 minus. So in part 4, I believe we use 5 mils, right? So we use 5 mils of the concentrated calcium iodate solution. Okay. So for part D, we have, so for our part D, we're going to calculate the molarity of IO3 minus. So molarity so we're going to take the moles. So molarity is moles over volume in liters. So we do 6.02 times 10 to the negative 5th molar. Oh, sorry, it shouldn't be molar. It should be moles. My apologies. Moles here. And we know the volume is 5 mils, but that will equate to 0.00500 liters. So if we divide that, we should find our molarity now, which should also be quite small, I think. So divided by 0.00500. Yes. Okay. So that's actually 0.120 molarity an iodate. Okay, so divided by 5 mils, that's actually 0.120 molar iodate ion. Okay. Now the next part is where we find the solubility of calcium iodate in pure water. So solubility of calcium iodate. Now, if you read ahead, if you read the so if you read ahead before the lab, in the introduction, it actually showed you how to look at this situate, how to set up an equilibrium expression, or I'm sorry, a ice table. Okay, so calcium iodate is usually solid, so we can represent this like so. Calcium iodate goes to, so we always use single-headed arrows because it's usually a small amount that goes to the ions. So we have calcium 2 plus aqueous plus 2 iodate ions in the aqueous state. Okay. So our initial conditions here, initial and final conditions. So remember, the solubility is so low, we just say that the initial and final for our solid here, so let's put a solid sign here. Our solid here, it's not going to change much. Okay, so we say initially it'll be solid, and the final state will be solid because the concentration doesn't change much. But in calcium ion, we'll have 0, and for iodate, it'll be 0. But we have to take into account the coefficients in front of the calcium and the iodate, because for every mole of calcium iodate, we have 1 mole of calcium 2 plus and 2 moles of iodate minus. So our change here will be X because it's 1 and 2X for iodate. Okay. All right, so to calculate solubility, I believe we'll have to first calculate KSP, unless it's given to us. I don't see a KSP expression for iodate here, so we might have to solve for it. Okay. Okay, maybe we don't have to do this yet, but okay. But as you recall, maybe in lecture, that the solubility X of calcium iodate, that will be equal to, the concentration, so the concentration of the calcium 2 plus ion. Okay. And that's because for every mole of calcium iodate, that dissolves, one mole of calcium ions is formed. Now we can say you could go based off on the concentration of iodate, but you then have to divide it by 2 because 1 mole of iodate contains 2 moles of 1 mole of calcium iodate will have 2 moles of iodate. So it's a 2-to-1 kind of ratio. So 1 mole of calcium 2 plus forms. Okay. So by that similarity, we can say that the now we know the moles of iodate. We can say, oh, if there's 2 moles of iodate, right? So the ratio is calcium iodate. So you see here that the ratio is 2-to-1. So we should say the calcium 2 plus concentration equals the solubility equals solubility of calcium iodate, and that will equal 1/2 the concentration of IO3 minus. So in this case, we're going to take 1/2 times 0.120 molar, and that gives us 0.0600 molar, and that's our solubility right here. Okay. So that's our solubility. Okay, so that's our solubility for this part of the experiment. Now we're going to calculate KSP. Okay, so iodate, we just take 1/2 of the concentration because in our chemical equation, it's calcium iodate goes to calcium and 2 iodate ions. So we have to divide by 2 to find the value for X. So remember, X is the solubility. And to do that, we have to take 2X, divide the value from X by 2 to get us the solubility of calcium iodate. All right, so now we're going to find KSP. Okay, but first, let's take a little break here. I'll be right back. Okay, so now welcome back. We're going to calculate solubility product of, calculate the solubility product, KSP, of calcium iodate. In pure water. So now here we have to consider the concept of activities. So this is based on activity. Based on activity. Okay. So we're going to use both concentration and activity. So what activity is, activity, when we say the activity of a ion in solution, it talks about the interactions, between ions in solution. So if there's any chemistry majors out there, you might learn more about activity if you take when you take physical chemistry or analytical chemistry. You'll definitely talk about what activities are. So it takes into account the interactions between ions in solution. So when we say, ions, they just behave by themselves, they're surrounded by water molecules, that is not the case. So we kind of lied to you in Gen Chem. We said that, the pH of the solution is just the concentration of H+. But that's not true. It is the activity of H+ in solution. So that is equal to the concentration multiplied by the activity coefficient at a specific temperature. And the activity coefficient is dependent on the ionic strength or the amount of ions dissolved in solution. Okay, so that's activity. So we're going to write out an equation, Okay, write out an equation calculating ionic strength. So this is the sum of all the ions in our solution. So we give this the mu sign here of calcium iodate. Iodate in pure water. So we assume that no other ions are present. In pure water, using the concentration So the concentration in our equation will be Ci and charge. Charge, which is Zi, capital Z for the nuclear charge, Di, of each ion. Okay. So first, let's go back up to the start. So if you go to the start of your lab manual, it'll show you the calculation for charge. So for our cases, it'll be okay, let's see here. Okay, let's see here. Let me see for 1 second here. Okay. Okay. Boom, boom, boom. Ah, I see. Okay. All right. So our calculation is mu equals the sum. So this is the summation sign of, so we're going to take 1/2. Let me just redraw that. 1/2 the summation sign here. I, or is where we start, Ci times Zi squared. So in our example, it'll be 1/2 times, so the calcium ion, we're going to do the calcium ion here. So it'll be the concentration of the calcium 2 plus ion times the charge of the calcium 2 plus ion squared plus the concentration of IO3 minus times the charge of the IO3 minus ion squared. Okay, and we take 1/2 of that and we'll get our answer. So 1/2, okay. So Z squared is 2, right? So we're going to have our concentration here, which is, so our concentration of calcium is equal to the solubility of calcium 2 plus. So we're going to use 0.06. 0.0600 molar. Now yours will probably differ because you'll lose your value you calculated in part 5. Okay, so we're going to do now. Let's go back here. Okay. Okay, so I actually skipped a part, but let's we'll go back to the other part again. Sorry about that. I kind of skipped parts here. All right, plus, so that's we're going to have 2 squared in this case because it's 2 plus. The charge of calcium is 2 plus the concentration of iodate, which is 0.120 molar, times minus 1 squared. Okay. Now, if we solve that equation, we will get a value of 1/2 times, so 0.006, whoops, 0.0600 times 4 is 0.24, so we get 0.24 plus 0.120 molar, and we get, actually let's just put the units at the end here. So we get plus 0.120 times 0.5. So we have an ionic strength of 0.18 molar. Okay, so that's our ionic strength right there. Oh, interesting. Okay. So we should have substituted this for X. So let's do that. So for this equation, you want to write the concentrations as your solubilities. So what we determined in our last section, we would have the concentration of X for the solubilities for the concentrations of our ions. So X times, now let's just put this 4. So it's going to be 4 times X, right? 4 times X plus, or in our case, let's say it's going to be 4 or 2 squared times the concentration of calcium 2 plus the concentration of -1 squared times the concentration of iodate in solution. Okay. Now we can rewrite this as, in terms of X, our solubilities. So in this case, it'll be 4. So let's just rewrite this completely. Let's write this as 4. And then this whole part will disappear. Okay. So 4, and remember the solubility for calcium is the same as our solubility for calcium iodate. So we get 4x plus, in this case, just 2x, right? Because remember the iodate concentration is equal twice the times the solubility, so we get 2x. Okay, so now we just plug in for x, we should get the same value for solubility here, or for our ionic strength. We get 6 times 0.00600 times 0.5018. That is interesting. Did I do that right? 0.06 times 6. Oh, okay, I did it wrong. Sorry. Yeah, that's correct. So we get, we can actually rewrite this as this. So it equals this basically. This thing is 4x, but it actually equates to 6x. Okay, so that is 6x. So it'll be 1/2 6x or 3x. And then we can simplify this equation even more to 3 times 0.0600 molar, and we get 0.18 molar. So that is our ionic strength right there. 0.18 molar. Okay. So now we go to our, so this was rewrite the equation using X. So this is part, so here's part B. So we're going to put part B here. And then part C is calculating it. So here's part C, calculating the ionic strength. Now part D is where we go to our table and the introduction and find the coefficients for calcium 2 plus and calcium iodate. So let's go back to our table in the front of here, table 1, and we'll look at the ions. So on our table, so ionic strength. So our ionic strength for a 0.18 molar solution. So now your table will give you values, but you need to choose the value. You need to choose the column it's closest to. So we're going to choose the column from 0.15 molar. Okay. So if we go down to the calcium 2 plus, we see it has a value of 0.36. Yeah, so 0.36. Activity for calcium 2 plus, we get 0.36. So that's just our coefficient. Okay. So we go back down to our calculations here. Okay. Okay, and then we need the one for IO3. So activity for IO3 minus. So for IO3 minus, we go back up, go back to the 0.1015 situation, and we see that the activity coefficient is 0.76. 0.76. Okay, so those are our activity coefficients. Okay, so now we're going to go back to our calculations here. All right. So now we have to rewrite. So if we go back to our coefficients here, if we look back onto the introduction, our activity coefficients, remember our equation we wrote up here, it's going to look something like this, x and 2x. So keep those in mind. So now for part E here, we're going to rewrite our equation, our KSP. So our equilibrium constant will be the activity. So let's put activity of Ca plus 2 plus here. 2 plus times the activity of, so when we have activity, we need to square it. For iodate in this case, there's 2 of them. So we're going to square it in our equation, just how you would square the concentration in an equilibrium constant. Okay. So gamma is the activity coefficient. So gamma equals activity coefficient. And I just realized how bad that was. So these coefficients are right here. Those are our coefficients. Okay, so gamma of calcium 2 plus times the concentration of calcium 2 plus. Okay, and then we're going to multiply that by the coefficient of iodate ion multiplied by the concentration of our iodate ion right here. Okay, and then we can simplify this now. Part F, we're going to simplify this into values of X or solubility that we just calculated. Okay, so this will be, so K now. So let's just label this as K. K will now equal, and this is, if you look at example your lab manual, it does go over this. So we can definitely, there's definitely another example you can use to follow along. So use gamma times the coefficient of Ka2 plus times times X, because remember calcium is going to be the same value as the solubility, X times the coefficient of iodate ion right here times 2x. Oh, so remember we had to square these. I forgot to do that. So we had to do the square and square the coefficient of the gamma right there. So it'd be both this squared times the solubility or the concentration 2x squared. And that's because, you know, there is twice the amount of iodate ion. Now we can further simplify this by calculating, you know, they both have x's, right? So we could take out the x and say it's equal to 4x cubed times the coefficient here of calcium 2 plus times the coefficient of IO3 minus squared. Okay, so that is how we would set up that calculation right there. To make life simpler, okay. So now we would solve for our solubility product by inserting our values. So 4 times x, which was 0.0600 molar cubed, times the coefficient of 0.36 times 0.76 squared. Okay, so that will give us a value of, all right, so let's go back to our handy calculator. So make sure you double check these calculations. 0.0600 cube times, so let's do 4 times 0.000216. Okay, and then we're going to times 0.76 squared times 0.36, and that gives us a value of 0.207936. So let's keep all the digits, multiply that by 0.000216 times by 4, and we get our KSP, which is 1.8 times 10 to the 10 to the -4. And if we look up the KSP value, let's see that right now. KSP of calcium iodate. Okay, calcium iodate. All right, so we're close. So the actual value, so the actual is calcium iodate is, oh, actually we're a little bit off. So okay, let me see. Calcium iodate 6.47 times 10 to the -6. It's a little bit off, but that's how you calculate the KSP value. Oh, okay. So I believe this is in pure water. But let me see if there's a more reliable source. So yeah, it's about 2.0. So that's interesting though. Zero point zero 0.060 cubed times 0.207936 times 4. Yep, that's it though. Okay. So I don't know. I don't know what the actual value is, but maybe it's 2. I think it might be 2.0 times 10 to the -6. Well, I should be using a textbook actually. Let me see. KSP values. Let's see. There's a better table here. All right, calcium. They don't have it very much for the iodates, unfortunately, but there should be a table here. Iodides, nope. Sulfites. KSP values for iodates. Okay, let's see here. Boo, boo, boo. Okay, so it's 6.47. So let's say 6.5. So our error is pretty high. So hopefully your data is a little bit much better. But let me just double check everything that I did correctly. I did 1/2. Yeah, I think we did that. You know what might be the problem also is because we extrapolated our value. We looked at the 0.15 molar. So the numbers will probably be off. So hopefully your ionic strength kind of fits through one of those categories. But for your ionic strength, use the activity coefficient that matches closely to your ionic strength value and use that for the activity coefficient. So if we were to do activity coefficients, we can actually look it up. There should be a table of them somewhere. Table, activity coefficients table. So we do look that up. It should give you more proper values, but in this case, let's not worry about it too much. Okay. If I can open this document here. Okay, moles. Okay, never mind. This is not what I want. So activity coefficients. And they had to choose this last experiment with lots of calculations. Yeah, so for activity coefficients, we just kind of have to extrapolate it. They are known, but they are not known to the exact value of our ionic strength. So we just have to make do with what we have. So 0.1, it has 0.15, so that's why we use that one. Okay, so now let's move on here. So now we're going to go a little bit back. Let's go back to where we determine the solubility constant using concentration. So calculating. Calculating solubility products. Now my numbers will be weird because, as I said, I made the numbers up. I don't know if that's exactly true. But I did go around class and get some numbers so I can have an idea like what students should be getting. So calculating solubility product, KSP, okay, of calcium iodate. Of calcium iodate. impure water. Impure water based on concentration. So now we're going to use concentrations based on just concentrations. So this part, we're just trying to compare our values based on the concentrations and the activities. Okay. So when we do on concentration, we assume that the coefficients are 1, so they have no influence on the activity of the ions. So this is very similar to what we just did. We will use the equation that, remember, K equals the concentration of calcium ion plus times the concentration of iodate ion. And that's it, because remember, if we go back to our equation here, calcium iodate is a solid, so it doesn't appear in our equation because we assume that the calcium iodide, not much of it is going to be changing. So we say that it's in unity, so we put this all over 1, and this is the unity value, so unity for solids and liquids. Okay, so we just assume that the change in their concentration won't be much, so we assume they have a ratio of 1, so they don't change. Okay, so that's 1. All right, so we can express this in terms of x now, and we did that here. Oh, it'll be squared here. Apologies. I just can't get over this fact that it's so low. I wonder what's wrong. Okay, but that must be it. I still can't get over this value here, but it's probably because I made up the numbers. So your numbers, I would hopefully be much more accurate. Yeah, so I think we're right. Okay. So if we look back to our equation here, we saw that it was x and 2x. So see, our final value should be x and 2x. So we can substitute those values into our equation here. So K will now equal x times 2x squared. And if we solve for that, it'll be 4x cubed, okay? And then we can plug in our values here. So that is our expression, part C. We're going to solve for that expression. Equals 4x cubed, which equals 4 times our solubility, 0.0600 molar cubed. And that will give us a value of 0.0. Also, let me see if I did this right. First, let's go back here. So our solubility right there. 0.120. 0.06. Yeah, that is correct. You know, I wonder what happens if we put in, yeah, that is correct though. That should be correct. If our solubility of iodate is 2 times, then our solubility for X should be 1/2 that. So it should be 0.0600 molar. All right, so let's solve for that. 0.0600 cubed times 4, and we get 0.000864. Or 8.64 times 10 to the negative 4th as our KSP value. Okay. So these are the numbers. We are quite off, but not quite we're not near our value we want, but it's pretty it's decent. Okay, so that's the concentration. All right, so we did calculate product KSP based on activity and concentration now. Now let's determine, now let's go to experiment 4. So these were, experiment 5. So these were all part for experiment 4. So hopefully that cleared some things up. Calculating the ionic product, calculating the solubility of calcium iodate. So hopefully we were able to solve some, or get rid of any confusions. Okay. So this will be the last step of the calculations, everyone, and then we'll be done with Chem 2. So just chemistry always has a lot of calculations. So determining, so this is part 5, determining the concentration. So determining, oops, that looks way too spaced out. Yeah, sorry, this video might be long. There's a lot of calculations to do and a lot to explain because I don't know if you guys have talked about activity coefficients in class. So it's a lot to do. Determining solubility, oh, sorry, not the concentration. Determining solubility. So determining solubility of X. So remember, when we do a KSP expression, X is always our solubility of the solvent itself. Of calcium iodate in 0.01 molar potassium iodate. So this will tell us this. This is what we call the common ion effect, and it actually makes solubility, I think, decrease. So we will study the common ion effect. So common ion effect. So the common ion effect is iodate. So the iodate appears in both solids, potassium and calcium. And we must know that 0.010 molar IO3 minus is from KIO3. So that's coming from KIO3 and not from the calcium. So it's not the calcium it's coming from, but it's the KIO3 instead. Okay, so part 1. So what volume of, so in our titration of, in part 5, you're going to, we're going to answer the volume of standardized So it's very similar to what we did here. Okay. The volume of standardized sodium. So there's actually a typo in here. It's sodium thiosulfate, not sodium sulfite. So sorry about that typo. Required to reach the endpoint. So I think it should say the equivalence point, but the endpoint, equivalence point. Yeah, so this assuming it's the same as the equivalence point, all right, or when the titration ended. So let's say our volume is, I don't know, 10.3 or 10.26 milliliters. Okay, so we're going to do the same thing we did in our previous calculation. Now we're going to take molarity equals moles over liter. Now we're going to solve for moles. Mole equals molarity times liters. So in this case, it'll be 0.0531 molar times 0.01026 liters. Okay, and we do that, we get 0.0531 times 0.01026, and we get 0.000545 mole sodium thiosulfate. So that is our moles of sodium thiosulfate. So on C, we're going to calculate moles of iodate. All right. So, and this is going to include, but also the moles of potassium iodate in solution. So remember, potassium iodate, very soluble in water. So we're going to assume that all of it dissolves. So we're going to take first our sodium disulfate. So remember, the amount is equal to not only the one from calcium iodate, but potassium iodate as well. So 0.000545 mole sodium thiosulfate, and we go back to this previous equation. We can just copy and paste our calculations here. Right here, 1 to 2. So we're going to copy and paste it here. Okay. So in this case, moles of thiosulfate. Let's just make this thiosulfate just so it's easier. S2O3 2 minus. So those will cancel out. Moles of iodine will cancel out. And then what we're left with is a value of 0.0000908 moles iodate. So that's how many moles of iodate was in solution. 1, 2, 3, 4, 5. Yeah, iodate in solution. All right, good. So now D, we're going to calculate the molarity. So the molarity of potassium iodate. Calculate the volume. Or we could just leave it out as not potassium iodate. We have to leave it as IO3 minus because there's two sources of the iodate ion now, potassium and calcium. So we take our moles. Mole of iodate. And if we go back to our procedures here, we should have used 5 milliliters. Okay, so we used 5 milliliters. So 0.00500 liters of solution. Now, if we divide up our moles by 5, or by that small number, we should get a value of 0.0182 molar. of IO3. Here we go. That's the molarity of this part of the experiment. Okay. Okay, so now let's make another ice table for part E here. We have now the calculation is, or the equation is KiO3, calcium iodate, it's a solid, is going to calcium 2 plus aqueous plus iodate ion, 3 minus. 2 iodate ions because in the chemical formula, it's producing 2 iodates in solution per given calcium iodate. And now we have our initial conditions. Let me just move this over a bit. So our initial conditions and final conditions. So calcium iodate will remain a solid, and this calcium iodate will also be a solid. So only some of it will get into solution, right? So the solid that, the solids were in the bottle. So the solution is we need to find out how much of it was in the ion form. So in calcium, it's going to be X, because we don't know the calcium. So for calcium, it's 0, right? And 0 as we start out the reaction. And then as the reaction goes forward, it'll produce some calcium. That's going to be X. But iodate is a little bit different because we had initially in solution, there was already 0.010 molar. So now we had to add that to our final value of 0.010 molar plus 2X. Okay, so now we have to solve for that. So our total concentration is going to be, so concentration of iodate minus equals 0.010 molar plus 2X. So we need to solve for X, because our X value will give us our solubility for calcium, and therefore for calcium iodate. So let's solve for that right now. Plug in the calculation, the numbers 0.0182 equals 0.010 plus 2X. So if we solve that, we will get 2X equals 0.0182 minus 0.010. That gives us 0.0082. And then divide this number by 2, we get the solubility X equals 0.0041 molar. So that equals our calcium concentration, 2 plus, which equals our solubility for calcium iodate in this solution here. Okay, so 0.0041 molar. Okay, so if we compare this, that's much smaller than our part 4 calculation, where our concentration was is 0.006 molar right here. Okay, so very much smaller, and that's due to the common ion effect. Okay, so now we're rolling into the last two calculations here. Calculating KSP for both based on concentration and then based on ionic strength and activity coefficients. So I think the calculations are pretty much the same, but let's go over them. Calculating. So calculating solubility product. So feel free to watch this video as you do the post lab, or just come by and check to see if you did it correctly. Of calcium iodate 2 in 0.01 molar KIO3 based on concentration. Okay. So remember, our equation is K equals calcium 2 plus times the iodate concentration minus squared. Okay. So this is part A. So we're writing our expression. So here's our expression for KSP. Okay. So now we have to rewrite it in terms of X. So we're going to rewrite it in terms of X for calcium iodate. So we're going to write K equals X times this one squared. But remember the fact that there's iodate concentration from the potassium iodate. So we need to account for that. So that is going to be 0.010 molar plus 2x squared. Okay. So now this means we're going to solve this equation. So this can equate now to, okay. So this gets a little bit complicated. But instead of expanding it, it might just be easier to plug in everything in one go. So let's do that. See, now we're going to solve for it. K equals X, which is 0.0041 times 0.010 plus 2 times 0.0041, and then square that whole bracket there. So if we do that, our KSP is, okay, 2 times 0.0041, okay, and we're going to add now plus 0.010, square that whole value, multiply by 0.0041, and we get 1.4 times 10 to the 1, 2, 3, 4, 5, 6. 1.4 times 10 to the negative 6. So that value actually looks a lot closer than part 4, where we calculated it off by a factor of 2, orders of magnitude of 2. So this is our answer here. 1.4 times 10 to the negative 6 as our KSP. Now you could expand this equation. It will be 4x squared plus 0.040 x. Yeah. Right. And then plus 0.010 times 2. No. 0.010 times 0.010. 0.001. 0.001. Nope, actually 3 zeros. And then you times this whole by x again. You times this by x again, it'll be 4x cubed plus 0.040 x squared plus 0.001 x. Now, if we solve that, it should give you the same number, I think. 0.0041 cubed times 4. Yeah, but it's a very complicated number. Let's see here. Plus 0.0041 squared equals plus 0.0001 times 0.0041. Well, maybe I did something wrong, but yeah, it gives you something completely different. Let me see here. 2x plus 0.010 times 2x plus 0.010. So you have 4x squared plus, let's see here, 0.010 times 2. Oh, okay. Wait, no. Plus 0.040 x. And then you get 0.010 times 0.010. Yeah, you get plus 0.0010 x. Okay, so we solved these four, and then it's still times it's still times by x here. So you get 4x cubed plus 0.040 x squared plus 0.0001 x. Okay. So 4 times, so 0.0041 cubed times 4, that's about 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So that's 2.76 times 10 to the negative 7 plus 0.0041 squared times 0.04. That gives you 1, 2, 3, 4, 5, 6, 7 plus 6.72 times 10 to the negative 7 plus 0.0041 times 0.0001. That gives you 1, 2, 3, 4, 5, 6, 7. So that's 0.12. Well, no. 4.1 times 10 to the negative 7. So if we add those all together, we should get the same value. Plus 2.76 e to the 7 negative. Okay. So yeah, you get the same answer. 1, 2, 3, 4, 5, 6. Yeah, so you get the same answer. So this is the same answer. So there's two ways you can do it. Obviously, one of them is, I think, much simpler, but if you expand it correctly, you can do it as well. So this is based on concentration. So 1.4 times 10 to the negative 6, a much closer value now. Now let's go to, it's probably because I chose a better number, but you'll use actual numbers in your calculations. The last part of these calculations, calculating solubility product. Well, I did not expect these calculations to go so long. So remember, everyone, you need to spend your time wisely because these calculations can take a lot of time. So it's important that you do not do these to the last minute. Just like learning, teaching as well does take time and effort and patience. So you can't rush things. KiO3 based on activity. So now we're doing it based on activity again. Okay. So these calculations will differ slightly from the previous section because now we have more KiO3 concentration. So in this case, now we have to consider K plus. All right, so we're going to go based on our ionic formula here again. So we had 1/2 E Ci squared. So it's going to be ionic strength is 1/2 I, so Ci, and then Ci. Let's go back, make sure we're calculating it correctly. Ci squared. Okay. Yeah. So Zi squared. We'll go back here. That's the equation we use. Yes. Okay. Okay. So, all right. So remember, we have a lot of things to consider. So mu equals 1/2 times the concentration of calcium 2 plus times the charge of calcium 2 plus squared plus the charge of iodate squared plus the concentration of potassium now and the charge squared of potassium. So we had to use both. Okay. So that's our concentration. Now let's rewrite it in terms of our solubility X. All right. So mu will be equal to 1/2. The concentration of calcium was 0.0041. And then the charge of calcium is going to be 4 squared, right? So it's going to be 0.0041. Oh, sorry, we could just do this. So concentration of calcium 2 plus. And that will be 2 plus squared plus the concentration of iodate times the charge, -1 squared, plus the concentration of K plus times the charge squared. Okay, so let's rewrite these in terms of x. Equals 1/2. So in this case, it will be 4x squared. So we have 4, well, not squared, but 4x. So concentration of this turns into 4 times the concentration of calcium, which is x, plus the concentration here of iodide ion. But remember, iodide ion is a little bit different in this last example because we already had initially 0.010 molar. So it's going to be 10 molar plus 2x. And then lastly, we have plus potassium, and potassium will just be x as well. Okay, so no. So in this case, potassium will be the amount of potassium we added, so it's 0.010 molar. And since it's multiplied by 1 squared, it just stays 1. There we go. So now we just plug in x for the solubility. You calculated in the previous step right here. So here's our solubility. Solubility in the previous step, which was right here, solubility, 0.0041 molar. Now we plug that in for x. So doing that, we will now solve for ionic strength in part C of our example. So here we're solving for ionic strength. Okay, so we have this is equal to 1/2 1/2 4 times 0.0041. So let's just make this in brackets. Plus 0.010 plus 2 times 0.0041. Put that in brackets again, plus 0.010. And then we're going to put that in parentheses times 1/2. So this equals 1/2 times. All right, so let's do this stepwise so it's easier to follow along. 1/2 times 4 times 0.0041, we get 0.0164 plus 0.2 times 0.0041 plus 0.010. That gives us 0.0182 plus 0.010. All right. We multiply that all out, we get plus 0.010 plus 0.0182 plus 0.0164. That gives us 0, so 1/2 times 0.0446. And we just solved that now. That will equal times 0.15, 0.02 molar. Okay. So now we solved for the ionic strength. Now let's use the activity coefficients. So in our KSP equation, we only care about calcium 2+ and iod 3-. So in this case, our activity coefficients for calcium, let's go back to our table here, all the way up here. So for 0.0, again, 0.02, don't really know how to extrapolate this, but let's go to the 0.01 column. I wonder if there's actually a table in our equation here. Okay, let's see, table here. Nope. Yeah, we kind of have to extrapolate here. We can't use the we can't actually use the actual value for our extreme, so we have to use the column that it's closest to. So in this case, it's probably closer to 0.01 molar. So we're going to use that column. And I believe in the instructions, they do tell you to do that. I hope. So calcium 2 plus. So in this case, in the 0.01 column for calcium, it will be 0.675. 0.675. And then for iodate, it'll be 0.902. You see, the less concentrated it is, the more closer to unity or one that it represents. Okay. So we got our ionic concentrations now. So now let's go back to this part. So now we have to rewrite the KSP expression using our constants. So KSP, or simply K, we're going to rewrite it as the activity. So activity of Ca2 plus times the concentration of Ca2 plus multiplied by the activity. Well, sorry, it's the so if we go back here, we said it was the activity of calcium and the activity of iodate. And so calcium, times the activity of iodate here, 3 minus. And then I believe we don't put the squared term until after. Oh, no, we do put the squared term. My apologies. Squared here. Okay. We can rewrite this as the activity coefficient of calcium 2 plus times, I just want to keep it in the same format. Okay. Yeah. Times the concentration of calcium 2 plus times the coefficient of iodate squared times the concentration of iodate squared. Okay, so if we go back here and just kind of confirm that, yes, iodate squared. Okay. All right. All right. No, E. So this was part D. This is part E. Now part F, we're going to represent this equation by substituting solubility X. So our equation should be written in terms of X and the activity coefficient. Okay. So now K would equal activity coefficient of calcium 2 plus times X for our solubility here times the coefficient for iodate minus multiplied by the concentration now, but remember the concentration is a little bit different. So it includes the amount of iodate, ion from the potassium iodate. So plus 2x. And then we're going to square this whole thing as well. All right. So now we're going to use the solubility and solve for the solubility product right here. So let's do that. G equals K equals the coefficient for calcium, 0.675 X times the coefficient here, 0.902 times 0.010 molar plus 2x squared. So I would leave it in this form. You can expand it if you'd like, but it might be just easier to just do it in this form. Okay. So we can definitely simplify a few things here. So we can, but it might just be better just to plug in x. 0.675 times 0.0041 times 0.902 times 0.010 plus 2 times 0.0041. Okay, and then square that whole parentheses there. So let's just simplify a few things and solve for the KSP, and then we will be done. Okay, so 0.675 times 0.0041, that gives us 2.7, let's skip a few digits, 2.77 times 10 to the negative third. Okay? Multiplied by 0.902. And now this fraction here, 0.010. So first let's do 0.0041 times 2 plus 0.010, okay? And then we're going to square that. And that gives us 3.31. 3.31 times 10 to the negative 1, 2, 3, 4. So negative 4. So that's the whole fraction after we write everything out. Okay. So now let's simplify things further. 2.77. Oops. 2.77 e to the third negative times 0.902 times 3.31 e to the 4 negative, and we get this value is 8.3 times 10 to the 1, 2, 3, 4, 5, 6, 7 negative 7. So now I have a value that is a little bit more off than the previous example where we just calculate concentrations. So you see here that the KSP now is has, if we compare it to no added iodate, it has decreased considerably. So the KSP has decreased considerably, but you know, when you're doing the KSP calculations, the common ion effect, it shouldn't actually, what it does, it actually does, I think it does decrease it, right? So the common ion effect on KSP here. Okay. Yeah, so even if you added some, it'll just shift the equilibrium. So the solubility will decrease, but that means that still the product of the ion, the constant should be the same. So we got closer to the value, but it looks a little bit off here versus the based on the concentration example. So what happens is the equilibrium shifts. So it'll shift to the right to form more solid in this case. So we perturb the equilibrium. It will shift to the right. Sorry, to the left in this case. So that's what will happen in this case. It'll shift. So shift to the left of the solid. So in this case, you see here that our solubility decreased. So what that meant is that some of it shifted to the left of the equation. So we go back up here. So if we were to write this as the equilibrium expression, this means that reaction. So so in this case, adding KIO3 decreases the solubility of calcium iodate. So that's what's called the common ion effect. You would also observe this effect if you added something like calcium chloride. It'll also decrease the solubility. So that's how we do the calculations for this experiment. That is it. Hopefully your numbers are much closer to the actual KSP. But you know, calcium iodate is not very soluble. So that's why we made a saturated solution. And saturated means you make a solution in water until no more calcium iodate dissolves. So if we look up calcium iodate, I don't believe it has a very strong solubility. Yeah, so in 100 mils of water, only 0.24 grams dissolve, so not very soluble. And the KSP is, yeah, 6.47 times 10 to the negative 6. So see here, hopefully your numbers are much closer, but you know, see titrations, we can actually determine the solubility product of a solid if it's unknown and to great accuracy. Now my numbers don't represent that, but your numbers definitely should if you did it very carefully. But okay, so those are all the calculations. They were long. Hopefully you watched this video on time. But that is it. Let me stop sharing here and let's go back to Zoom here. Okay, so that is it for this experiment. That's it for Gen Chem 2A. Hopefully everyone will get through the lab and pass the class and move on to 2B, which is being offered next quarter. And I'm not sure if 2C, I think 2C is being offered through the summer. So those are, you can complete the series during the summer and then take OChem in the fall if you have to go to OChem next. Hopefully not, but most science majors in animal studies, trying to be like any biology major pretty much, or any chemistry major, they'll have to go through some form of OChem, either the 118 series for health sciences or the 128, 129 series for chemistry majors and chemical engineering. But I will post this video onto Canvas through the media gallery. I'll also send you a link directly to the Zoom recording, and then I'll post it on my teaching YouTube channel if that's easier for everyone. Okay, but if there's any questions, hit me up email. I'm working on and then I'll have these in by the due date, and then that'll be the end of lab. And then next week we'll just meet for discussion, and that's it. And then the final exam is around the corner, and then there'll be spring break and a much deserved rest, I think, for everyone. Okay, so that's been redox titrations. You may see this again in different analyses when you have a different analyte, but very important take. That's why we kind of drilled these titrations this first quarter, because they're important. You'll see them again after you get out of school, go work. Maybe if you go work for a company, analysis lab, one of the national labs, or maybe just a lab technician, you'll definitely see these things again. So that's this experiment, and that's the end of all the labs in 2A. I hope it has been worthwhile. They, I know experiments are kind of dull sometimes, but titrations, you know, you need patience. You need to be able to, honestly, when I do titrations, I listen to music. So I played music that one time. So hopefully it made things go faster. But yes, you definitely need patience. You need to be able to get good data. And it does take time. So hopefully we all understand like the importance of titrations and why we need to be patient and always be aware of, you know, if our data makes sense, if there's some abnormalities in our data or something went wrong during the titration, we have to accept that and be patient and be willing to do 1 or 2 more trials. So it's important that we calculate statistics as well. But just don't. I'll see everyone on Friday, this Friday, and I will send out some reminder emails about what's due. All right. So that's the end, and I'll see everyone later this week.